All right, this is Physics 1C for September 8th. Let me grab my tablet. So this is the list of what we're talking about tonight. We're going to talk a little bit more Gauss's law. We're going to talk about conductors and equilibrium. And then we're going to get into talking about electric potential. That's our goal tonight. Hopefully by the end of today's lecture, you have some idea of what the term voltage means, of what a volt is, also what an electron volt is. But for now, we're going to start off by finishing up some stuff about Gauss's law. So with Gauss's law, we learned that there's a way to find electric fields by making kind of an appeal to symmetry. And this is another problem that's going to provide a pretty useful solution to us. So a plane of charge. What's a plane of charge? Well, a plane of charge is basically just going to be basically like a box, but we need to draw it like kind of three-dimensionally. So let's draw a plane, and let's have it be drawn kind of like this. Okay, and let's say that our plane is a metal of some kind. Hey, why is this not? Uh-oh. Tablet's not working. Oh, it's unplugged. Oops. That would explain that. Sorry about that. Need to find something I can unplug here. My computer doesn't have enough USB ports, and I was playing Tony Hawk this weekend, so I had to plug in a controller. There we go. It's working again. All right, so we have a plate. It's some kind of metallic plate, and it contains positive charges. They're distributed kind of evenly throughout the surface. Like this. Tony Hawk is also all about physics. It's completely unrealistic physics, but there's some physics in there nonetheless. All right, so we've got this object, and it has positive charges distributed throughout it. It says that as a uniform surface charge density, sigma. Okay, so sigma, just to remind you what that symbol means, is basically, you know, what it says, uniform surface charge density. But you read those words, maybe it doesn't make sense. It basically means if you take the total amount of charge, Q, that's contained on your object, and you divide by the area of the object. Okay. Now, we want to find the electric field due to this plane of charge, except we really want the plane to basically go on forever. So we're going to imagine that this plane has an infinite size. Okay, or that the region in which we're looking at the field is going to be, so we're going to basically say that this isn't just a plane of charge, but it's an infinite plane. Well, it says it right here. I'm sorry, I don't need to write that. Just noticing right there, it was kind of weird that it said just plane. Okay, so in order to handle this problem, we want to use Gauss's law. And Gauss's law requires that we produce some type of surface that we can enclose some charge in, right? And in this problem, there's really a lot of options of what we can do. But our goal is always to construct a surface such that it will make our life easier when it comes to using Gauss's law. So the type of surface that we're going to use could be a rectangular prism. That's definitely an option of what we could do. Okay. Why are we getting... What's going on here? Let me close this. It doesn't want me to move this. Is it because... Oh no. Do I need the select tool picked? Probably. There it goes. All right, so this is the type of surface that we're going to choose. Let's use a different color. Let's make it green so it stands out. So we're going to take this object. Ooh, so I have to keep doing that. That's weird. Whatever. So we're going to take a surface that's going to be like a cylinder. And it's going to be exactly as Ash said. We're going to create a Gaussian surface which encloses some of the charge of our object. So this is going to be one face of our cylinder. And the other face of our cylinder is going to be on the back side of it. So I'll just kind of draw it back here. And then we'll just use lines to connect the sides of this so it looks kind of a little more three-dimensional. Okay, so there's our cylinder. And it kind of goes behind the surface. So what I'll do is I'll just let you guys use your imagination that one piece of the surface is to the left of the surface and one piece is to the right of the surface. And then what I'm going to do is I'm going to go ahead and grab another picture that ooh, where is it? Here, let's just zoom out, see if I can find it. I know there's another picture over here. There it is. This is my bad drawing This is the drawing from the book, but I think it often makes a lot of sense to at least let you see how you might construct it otherwise. So here's our infinite surface, right? There's our Gaussian surface. I'll make this a little bit smaller. It has one side to the right of the plane. One side is to the left of the plane, indicated by the dashed lines. And then we're going to say, we know that... why do you only go through part of the infinite plane? You can't really go through the whole infinite plane, because it's infinite, right? Like, we can make the size of our cylinder as big or as small as we want. We just need to, in order to understand what the field is, and that's our goal here, right, is to find the electric field, we need to enclose some portion of it. Similar to what we did, and I'll pull up the picture from last week, when we did the infinite line, our cylinder only ran around some portion of the line, but it still worked out. We still got the right answer. So for this week, we're doing the same thing, except, you know, we're drawing our cylinder like this, basically. Does that answer your question? You can't possibly enclose the entire surface. You have to choose just a small portion of it. Okay. Now, the next thing to do is to say we need to use Gauss's law to solve for the electric field here. And so let's write down what Gauss's law does. Gauss's law says that the amount of charge that I enclose, or Q enclosed, of our Gaussian surface divided by the electric constant, epsilon naught, is equal to the surface integral over our entire Gaussian surface of the electric field, which is what we're looking for, dot product with dA. And dA, to remind you, is basically just a vector, and we'll use the arrow here because I can't draw straight enough. It's a vector that would point perpendicular and away from the surface. This vector I've drawn here would be what we call dA. And drawn on this figure also is the electric field E. And we already kind of know, and you could argue, but for a lot of reasons, why the electric field has to point to the right here. The idea is that if we were to draw our plane sideways, so if we looked at like an edge view of the plane, so here's our plane, okay? It has all of its, oh God, I hate when it does that. You know what, that's probably fine. There's our plane, we're looking at it on edge. If I was to draw electric field lines going away from the surface, just as they've done here, I would say if it contains a bunch of positive charges, our electric field lines are going to point perpendicular to the surface. And they kind of have to. Stop being too shaping. They kind of have to. The electric field lines have to point out and away. They can't really have any tilt to them at all. They have to just be parallel and all pointing away from the surface like this. That's how the electric field's going to look. And it's going to basically just come out like these straight lines like this. Coming out here, 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 right? All going to be parallel to each other. You can't really have any other way for them to point because since it's infinitely big, these lines just can't point at an angle, basically. It's not possible. You've always got enough positive charge above and below so that you can't really have a component that points like this, if that makes any sense. Because after all, there's an equal amount of positive charge down here as there is up here. So you'll always have the y components due to those charges canceling out. And we've seen that happen in a lot of problems that we've done. So all we're left with is these parallel lines. So if we make it so that the Gaussian surface that we choose has one side, right, that allows the electric field to pierce through that side, then you're going to get some contribution to the flux here. There are basically 3 or 4 parts, depending on how you count it, to our surface right here. Okay? There's going to be the 2 top, like this piece and this piece, like the caps, and then there's going to be the curved portion. Okay? So as we're doing this right here, remember that this is defined as flux, right? This in general, we call this the thing that we're calculating here is flux. So what we're going to do is we're going to look at the flux through the left face. We're going to call this side right here left. That piece right there, the part that's dotted. Plus, we're going to have the flux to the right side. And that's going to be this side right here. plus the flux through the curved spaces, or the curved surfaces. Okay? Those are the things we're going to have to look at. So let's talk about this one first. The flux through the curved surface. So if I was to come along and I was to draw, let's say right here at the very top of my object, if I was to draw a vector to represent the surface, that vector would point straight up. It always has to be perpendicular to the surface. At that location, the direction of the electric field would point parallel to the surface, like that. So that would be the electric field. And you'd have a right angle here between the two of them. So those field lines wouldn't actually pierce through the surface. The dot product will be 0, that's right. As two of you were saying. So the flux through the curved surface is 0. That's right. There you go. You get 0 flux here because E dot dA, remember the dot product, just to remind you, E dot dA means you're doing E times dA times the cosine of the angle between them. And if the angle between them is 90 degrees, you get 0 because the cosine of 90 is 0. So we're just left with the flux through the left and the flux through the right. So let's look at those, and let's go ahead and calculate what the integral here would be for them. All right. So on the right-hand side, we see that the electric field and the dA are pointing in the same direction, right? So this ends up just becoming E times dA, because the angle between the two of them, E and dA is 0. And then same thing for the other side. You're going to get the integral of EdA. Continuing on with the derivation, this electric field ends up being constant. So you could pull the electric field out here. And you're left with just integral dA, which is going to be A. So the first one's going to be EA. The second one's obviously going to be exactly the same. You know, you might think maybe the one on the other side would be negative or something like that. And like this one's maybe positive and this one's negative, but that's not going to happen because in both cases you've got electric field lines, right? And our Gaussian surface here, right, our Gaussian surface is basically containing these things. So our dAs point like this and like this. And so you get positive flux on the left and positive flux on the right. The only way you get negative flux is if the flux goes inwards. Oh yeah, and I should also mention the electric field over the surface that we're looking at here is constant. The more lines I draw in here just makes the picture look worse. If the electric field wasn't constant, you'd have to integrate. That's right. If the electric field was different along the surface that you'd drawn, you would have to integrate. So for example, if you'd chosen a surface like maybe a prism, but you made it so that it was like angled like this, like that, then you'd have these different angles and probably different values, you might think, of the electric field at every point here, and then you might have to do the integral. But the goal of doing these Gauss's law problems is to never have to actually do the integral if possible. And if you do have to do the integral, you want to simplify it as much as possible. I know that on one of the one of the lab manual problems I gave you, you do have to do a bit of the integral, but it ends up being really easy to do. Just setting it up is the hard part. So that's what we're left with here, right? The left-hand side of our equation, we need to deal with this now because we need to calculate what Q enclosed is, keeping in mind that our surface is a uniform surface charge density with charge per unit area sigma. So maybe you guys can tell me, what would Q enclosed by our Gaussian surface be then? How much charge is enclosed? What could I do to figure that out? It needs to have sigma in it, and it probably has to have the area in it too. Sigma times 2 pi r, no, or pi r squared, that would be right. However, we didn't mention anything about the radius of this. We're just talking about what the area is, right? So we could just say sigma times a, right? And if we knew the radius, it would be sigma times pi r squared. It's just a, though. We'll just call it area a. So there we go. So our left-hand side of the equation, we can plug in down here. Sigma a divided by epsilon naught. Okay, and then let's write the last part of this here. The areas cancel out. There's 2e on the left side, so you end up getting sigma times, oh, we already canceled the areas out. Sigma over epsilon naught is equal to 2 times e. Divide the 2 over, and you get sigma divided by 2 epsilon naught equals the electric field. And this is something that we did in chapter 22. You could have picked the radius for sure. I'm just saying that it's redundant. Like I could write this as e times pi r squared plus e times pi r squared. And then I could plug it over here, pi r squared. It's still going to cancel. It doesn't. There's no point in doing that. You can, though. I mean, it's up to you. It's not like it's forbidden for any reason. But this is what we get as the answer then. And this is a solution we already had, but it's handy to know that you can also solve it with Gauss's law. Because if you make these problems like a little bit more complicated, solving them in the methods we did in the previous chapter becomes really hard. But solving with Gauss's law is always going to be pretty simple, if it's possible. So this tells us the electric field on both sides of the plates is sigma over 2 epsilon naught. It is uniform, meaning it doesn't matter. The only thing that shows up here is the density of the charges. The more densely packed the charges, the bigger the electric field is going to be. Everything else here is a constant. 2 is a constant, epsilon naught's a constant. So the electric field is uniform, and it doesn't really matter how far away you get, as long as you don't get so far away that it stops looking like an infinite plane. The solution that we come up with here is really for like a situation where you have a surface and you're close to the surface. Okay? You have a surface and you're close to the surface. Repeat what? How the area canceled out? So the area showed up in the electric field right here. The right-hand side of the equation. And it showed up in Q enclosed. So the area showed up in every single term. So you can cancel all the areas out. All right, this is the solution. And, I mean, it's kind of interesting. It doesn't really matter how far away you are. You'd think it would get weaker and weaker the farther you go away, but it doesn't. Does anyone want to maybe make a statement as to why that would be true? Why is it that it doesn't seem to... It's because it's infinite, yeah. Infinite plane, infinite sheet, yep. No matter how far away you are from it, it's still infinitely big, basically. All right, do you guys have any questions? Yep. That's right. Okay. So, and I'm wondering if they're part of the reason why... No. Discord settings have nothing to do with OBS. Never mind. All right. I do have this thing that says gain. I wonder if I turn that up if that changes things. I don't know. All right. So what we're going to do now is we're going to kind of try to use the knowledge we have of Gauss's law combined with an understanding of what a conductor is. And we're going to try to describe some interesting properties of conductors in electrostatic equilibrium. Okay. Now, I could write these all out for you, but okay, why is the little thing on the bottom? And now I clicked on that by accident. I'm sorry. Okay, so there it goes. So I pulled this list from another textbook. Your book mentions these things, but it doesn't. What's it doing right now? I have to click on that part first. Okay, there we go. So I could have just written these all down one by one, but what instead we're going to do is we're going to use each of these. What I want to do is I want to close this. I want to zoom in so that stuff can't see it. We're going to go through and prove every one of these. And in general, what we're talking about here is conductors in electrostatic equilibrium. These are properties, basically. And they're useful for solving certain types of problems. All right. Let me make this a little bit bigger here. All right. So these are the 4 properties. Let's read through each of these, and we'll go through them one by one and prove each one of them. So what's a conductor in electrostatic equilibrium? What do I mean by that? What I mean is, I have some conductor, and it's just a piece of metal, okay? It could be a sphere, it could be a rectangle, it could just be some arbitrary shape. So I've got some object, okay? And I tell you that it's a conductor, meaning that it allows charges to freely move within it, right? And then I tell you, I place some amount of charge on here in some way. How do I do that? Maybe I rub this object a bunch. I haven't even... Why the charge stays as surface of the conductor. We'll get to that. That's what we're going to prove right now, Ash. So I tell you that I put charges on here, and the question is, how do those charges distribute themselves if it's a conductor? Do they uniformly spread throughout the interior of the object? Like, do they just kind of go everywhere? And the answer is no, that's not what happens. Do they all go to the surface? And the answer is yeah, that's what happens. For some reason, they all go to the surface, and we want to kind of figure out why that is, along with some other things. So let's read through each of these and think about what they say. The first one says, the electric field is 0 everywhere inside of the conductor, whether the conductor is solid or hollow, so that you could have a hole in here, for example. So this would just be air or something, and this was metal. And the claim is that the electric field is 0 everywhere, inside. The electric field here is equal to 0, the electric field here is equal to 0. Okay. All right, that's one statement. The second statement is, if the conductor is isolated and carries a charge, the charge resides on its surface. So that means that all of the charges automatically go to the surface, basically, and only the surface. Some of them could go to the interior surface too, but it has to be on the surface. All right. The third part is the electric field at a point just outside a charged conductor is perpendicular to the surface of the conductor, has magnitude sigma over epsilon naught, where sigma is the surface charge density. And we just proved a second ago, you can scroll up so you can see it, that the electric field near an infinite surface is this. The electric field to an infinite surface is this right here. And we're going to say here that the electric field near the surface of one of these things is kind of like somewhat related to that, and we'll prove as to why. And the fourth one states that on an irregularly shaped conductor, the surface charge density is greatest where radius of curvature is smallest. We will not be able to prove this one today. We might. I doubt we'll get to it, but we need to develop the idea of electric potential first before we can get to this. So we'll prove the first 3. And we do this because it's definitely going to help you to solve certain problems, okay? All right, let's do number 2 first. 2, I believe, is the most logical one to start with, personally. So what we're going to do is we're going to look at a sphere, really a circle, I guess. So I take a circle. But it's really loving to get stuck on that draw thing there, isn't it? And I tell you that I place some charges on here. Now, first of all, let's say that I place 3 charges in here, okay? Just exactly 3 positive charges, all right? And I try to put one here, I try to put one here, and I try to put one here, keeping in mind that this object is a conductor. Now, you know that if these are the only charges that exist in this object, right, that there's a force that exists between 2 positive charges that repels them from each other, right? So that means that they're not going to stay here, right? They're basically going to get forced apart from each other until they can't really get pushed apart anymore, right? So I would argue that these charges, what they would do is... What they would do is they would spread themselves out as far as they possibly can to something like this. Did you guys agree with that statement? Does that seem logical? And as you put more and more charges on here, they're just going to spread themselves out as much as they possibly can. So if I put 6 on here, they're going to spread themselves out like this. Now I'm only really looking at this from a 2-dimensional perspective. In 3 dimensions, where they position themselves is going to be a little bit different. But the idea is they have to try to get as far apart as they possibly can. And as long as there's nothing that allows them to like get out of the surface, like if I tell you that it's extremely dry and there's very little humidity, and the charges, it's difficult for the charges to escape the surface, they're just going to push themselves as far apart as they possibly can. question is, if the charges are distancing themselves, wouldn't that... the word you used there is, did you mean continue? You look at what you wrote, there's a word there that doesn't, it's not a word. Constitute. If the charges are distancing themselves, wouldn't that constitute work? Yeah, I mean, what's wrong with that, though? One charge does work on the other one to cause it to move. What's wrong with that? You're getting way ahead. I mean, you can't use words we haven't even defined yet, Ash. That's not a good thing. So meowers, yeah, they naturally move to the outside. Okay, so that's effectively kind of like a proof. There's other ways you could prove this if you want to, but you could prove it using number 1, but I like to start with number 2. So if it carries a charge, the charge is going to end up on the surface. That's basically what happens. You don't get any charges inside. All right, so let's so we've kind of proved this in a way. So let's look at number 1. This says that the electric field is 0 everywhere inside the conductor, whether the conductor is solid or hollow. All right. There's 2 different ways to prove this. One, we can use number 2, and I'll try to not use it and we'll use it. Okay, so suppose that we want to think about what the electric field is in the region inside of the conductor. In the region inside of here. Okay. And we kind of say something like the following. What if the electric field was not 0 inside? So let's try to prove this by assuming the opposite is true. Okay. What if the electric field was not 0 inside? So what if I told you that the electric field in the region inside of this object was like this? Some uniform, I don't know, something like this. Let's say that it's something like this. What would that mean about all these other charges right here? They would feel a force. And so they'd kind of move to the right. Right? But that would kind of violate the idea that they're in equilibrium. Meaning that this would, if there was some electric field in here, it would kind of constantly move the charges to the right. And here's the thing, like, if this electric field existed like this, and it caused these charges to move, right? Any excess positive charges are going to kind of start to pile up on the right-hand side, right? Does that make sense to you guys? Like, if I told you that there was some electric field inside the conductor, and it caused the charges to move, it would push all the positive charges to the right-hand side, right? Not only that, it would also push other positive charges to the right-hand side, so you might even end up with more charges, even though we only started with, what, 6 of these. It's going to push additional charges over here, too. You're really going to get just a huge pileup of positive charges on the right-hand side. Now, the reality is the only way to make something like this happen is to have an external source that's making this happen. What could it be? Well, we just saw that if you take something like this, where you put positive charges over here, like a plate, and you on the other side, and you put a bunch of negative charges over here, right? This is going to construct an electric field, just like what I've described here. Does that make sense? This would make this electric field inside not be 0, right? However, what happens is that as a result of pushing all these positive charges to the right-hand side, what happens on the left-hand side over here? It becomes negative, exactly. So now what you've got is on the left-hand side, this face over here is now going to become more negatively charged, okay? But the system could technically still be in equilibrium now, okay? Except something additional has happened here. Because you've separated charges positive on the right and negative on the left, you've basically constructed another electric field, right? And it turns out that this process will happen. God, I hate doing this without like a ruler or something. This whole process is going to happen until the electric field, due to the charges on the inside, cancels exactly with the electric field due to the charges on the outside. So when subjected to an external electric field, the charges will move, but they'll move such as to make the electric field, the net electric field inside of here, 0. Did that make sense to you guys? So if there was an electric field inside of here, what would happen is that the charges would basically just move until the field inside became 0. Does that make sense? It's kind of a complicated explanation. It's like if the field inside wasn't 0, yeah, exactly, Nathan, that's a great way of putting it. It creates a new equilibrium. I apply some external fields because it's really the only way to produce an electric field in here. And the effect is that the charges basically just keep moving until the electric field inside is 0. And that's pretty cool. Now that's one way to prove it, but there's another way that's a lot easier. I think that's kind of complicated. That would be the way you'd prove it without using number 2. If you want to use number 2, though, why does it prove it's 0? The whole point is that if you produce without a charge, because so with the okay, your question is why does that prove that it's 0 without a charged plate on both sides? The answer would be the only way that you could. God, I hate this. Normally it defaults to this thing, so I can just select things. The only way you could produce these green lines here was to say that there was something external producing it. Yeah, it's only possible to produce these things with an external force of power, but then the effect is that as soon as you do it, you get this right here. We can talk about exactly what happens when there's no external field, though. When there's no external field, okay, we said that this is true. If there's charge, the charge resides on the surface, right? So we put all the charge on the surface. Let's say we put our 6 charges in here, we put them on the surface, right? And we want to prove the electric field inside is 0. So now what you do is this. You use Gauss's law, and you say, suppose that I want to figure out what the electric field inside of the surface is. So what do you need to do according to Gauss's law to do that? Well, you need to draw a Gaussian surface. So we draw a Gaussian surface inside of here, and we say, okay, what's the electric field going to be on the outside of that Gaussian surface, right? We say, what's the electric field at this location going to be? Well, if the charges have already oriented themselves so that they're all on the surface, then what's the charge that's going to be enclosed by this Gaussian surface? It's 0, right? Okay, well, if the charge enclosed by the Gaussian surface is 0, that means the electric field has to be 0 too. That's the way to prove it that I think is a lot easier to understand. As long as you understand Gauss's law, there's no charges inside, therefore the electric field inside 0. But even if there was some electric field that was produced externally, and that's kind of the second half of this, the charges would reorient themselves because it's a conductor, and they can move as much as they want to until the electric field inside was 0. One of the practical applications of this is that if you are inside of a conducting object and you're struck by lightning, let's say you're in a car and your car gets struck by lightning, you're going to be safe inside the car. Because the electric field inside the car, even if the body of the car becomes electrically charged, you're going to be safe inside. We have some nice demos for this at the school. I can't show them to you here, but... So the safest place to be inside of a storm is inside of a car. And mostly it's because all the charge will basically just stay on the surface. Okay? So that's the second piece of this. And that's the connection to the, if you're inside of a... So there's a picture in... Which book is it in? Is it your book or... There's this picture of someone in like a metal suit getting electrocuted, and they don't feel anything. The demo that I do at school, what you do is you take, and maybe I just found it from some book. The demo that I do at school, what I do is you take a box that's made of metal, and inside of the box you plug in what's called an electrometer, which is basically just this little device that has a metal piece up here, and then we saw this in one of the videos. There's little leaves down here that hang off that kind of indicate if there's... It looks like a person, but it's a metal ball and there's a leaf. We call it an electroscope. You place the entire system into a metal cage, sometimes called a Faraday cage. So the word Faraday cage basically just means an enclosed cage that's made of metal. So you have this this cage of metal. And then what we do is we take like a shocker. I don't know what it's called. It's just this. It's this like a needle, and it comes down to like a point like this. And then we plug it into a wall socket. So you got a wall socket right here, and you plug it in. And it's basically just like what you would expect would happen if you take a piece of metal and you plug it into a wall socket and it's connected to another piece of metal. It basically just creates tons of sparks. And these sparks basically just kind of like interact with this here. And I basically drag this piece all across the surface. And what happens is these leaves are never disturbed. 741. Here, let me see if I can pull it up real quick here, because I have the book up. Okay, I'm way ahead, but I'll find it. 741. Thank you. Is it from the previous chapter? I guess it is. Yeah, there it is. Okay. Here. Let's pull this over here. I thought it was in your book. Here we go. This is basically the demo we do. It's just, we don't have a big human-sized cage to use. But literally this thing is just producing these shocks. They go directly to this thing, but then the energy just kind of, all the extra charges just end up only in the cage. So, if you wore a suit of conducting metal, you couldn't get shocked. That's right. Yeah, that's the idea. Yep. And you'll notice that this, like, this suit the person's wearing, like, there's air gaps in it. You'd think that would matter, but it's the way electricity works, is that it's gonna want to go to these conductors here. All right. This is a picture right here of what I was trying to draw too, where it says that if you have an external electric field, the effect is that the negative charges end up on one side, positive charges on the other side, and the inside is zero. I think if you touch it, you're not safe, but I could be wrong. I'm pretty sure if you touch it, you're not safe. But since everything stays on the outside, you might be okay. Doesn't seem like you'd be okay, but I have to think about that. I wonder. You would need to have a path through which the electricity can flow, so it depends on like what kind of shoes he has here. I think if you grab two sides of the cage with your hand, you might be able to get electrocuted. But if you only grab one side, you might be okay. That's what I would think. I could be wrong about that. It's like you can, if you're working on a car, for example, you can get electrocuted if you like touch two pieces of the car, like the hot piece of the battery, like the red part of the battery, and you touch a piece of the car. You can get electrocuted then. But that's a different situation. The reason why they don't get shocked when they land on power lines, well, the power lines are insulated, right? So like the birds are standing on rubber. I don't think they could get shocked, right? Unless the power lines are just completely made of metal. Are some power lines just exposed to the air? They're not shielded? Maybe. Yeah, that's what I would think, Nathan, is they would have two contacts, but it says if you're in a conducting box. What does it say, Ash? Car is struck by lightning, the charge tends to remain on the metal skin of the vehicle. Little or no electric fields produced inside the passenger compartment. 771? Do you want to go 771? Okay. How do birds sit on high voltage lines without getting an electrical shock? Okay, we'll pull that up, Meowers, and we'll look at that. So exposed high voltage wires. Paragraph 2 of this page. I guess you mean the second full paragraph? Okay, so if the cavity... So yeah, I was kind of wrong with one of the things I said. But so the cavity is going to be like the inner surface, right? The only thing about the other picture that we were looking at was... It's like, what is inside when it's a cage, you know what I mean? This is talking specifically about... Yeah, I don't really know. Oops, where do we go? 771? Yeah, so the idea here would be that, yeah, maybe it is safe to touch the inside wall. Could be the case. I would be personally kind of worried if it was thin, though, because then, yeah, I don't know. Maybe it does, though. I don't know. The cage just feels like maybe it might be a little bit different. I definitely do not know the answer to that question. But if it's like your car and you have a thick layer, I think it would be okay to touch the roof of your car, for example, from the inside at least. All right, let's look at what Meower's pulled up here. How do birds sell on high voltage power lines without getting electrocuted? Let's see what this says. So the high voltage power line is at 1 voltage, right? So if they have 2 feet on the same power line, there's no change in voltage. Is that the idea, Meowers? That's what they're going to say here? They need a difference potential. Yeah, that makes sense. Okay. We'll talk more about this and the idea of what a ground is. Well, it doesn't just have to be the Earth, right? They need a connection to something that's lower voltage. The Earth could be one of those things, for sure. They're also saying the pole could be one of those things, too. It can be anything. You need something... the air is different, because it's an insulator. So it's just touching the air isn't really going to work. Yeah, air can be polarized, but it's kind of a different thing. It can, but not nearly at the level of, like, a metal wire. Like, it's not even close, so... Yeah. Have to think about this for a second. Alright, so we've proven 2 of these things. I really appreciate you guys participating and giving feedback and kind of questioning what I'm saying, because it's definitely all really good stuff for classes. So, do you guys have other questions about this before I go back and try to talk about the other 2 things here? Or specifically, we're going to do this number 3 one here. No? All right. So the 2 things we proved are that charges go to the surface and that the electric field inside the conductor is 0. An additional piece that was kind of brought up in that segment in the book is that if you had a surface like this here, that the electric field would be 0 inside. So they're claiming that you don't get charges on the inner surface here, right? Is that what it said? Or did it just say that the electric field in here was 0? That's the part that I got a little confused about what they were saying. Oh, the field inside the cavity is 0. Not that there's not charges on it, though, right? It is possible to have charges here, I believe. But the field inside the cavity itself will be 0. Well, I say that because we're going to do a problem where we actually talk about charges on the inner surface. I'm virtually certain you can still have charges here. But you need to have something else in here to make it happen, though. So actually, it probably makes sense that if there's nothing in here to draw the charges inwards, like a negative charge, then they'll probably all go to the surface. That's probably what's happening there. The charges want to be as far apart as possible. Yeah. Essentially. I think so. Alright, let's talk about this third one here before we go on break. Okay, so the last piece of this is the electric field at a point just outside the surface of the conductor is perpendicular to the surface of the conductor, has a magnitude sigma over epsilon naught, where sigma is the charge density. To prove this one, what we'll do is, here, let me move this down here. So we have a conductor. It's shaped however it's shaped. So here's our conductor. It carries charges. All the charges are on the outside of the surface. And what we want to do is we want to prove that the electric field outside the surface is sigma divided by epsilon naught. We also know the electric field inside the surface is 0. So what we're going to do to prove this is we're going to do something similar to the very first problem that we did today. We're going to surround our surface at one of its flat parts with a Gaussian surface, like this. Often referred to like as a Gaussian pillbox. So the surface on the top is A, the surface on the bottom is A. And now we want to figure out what the flux through the surface is. So we know that there's going to be electric field lines that point away from our surface here. They point kind of like this. We know on the other side, the electric field on this side is equal to 0. Right? We know from Gauss's law that, and this goes back, I'm just going to start from one of the lines that we had at the bottom. The charge enclosed by our surface is going to be the charge density times A divided by epsilon naught. This should be equal to the flux through our surface, which is just going to be the electric field multiplied by the area. In the previous problem we did, we had plus EA, one for the top side and one for the bottom side. But for the bottom side, E is equal to 0, so we don't get this piece right here. That doesn't exist. I must have changed something about the default. So this piece isn't here. So you can see what the answer is. You get that the electric field near the surface is just equal to sigma divided by epsilon naught. And that's the third one. Alright, so we've just proved this one. And we'll try to prove the fourth one probably on Thursday. The fourth one basically says, at places where you have really sharp points, like here, the electric field is going to be the largest. Oh, I got to prove why it can't be perpendicular. That's my bad. So the reason why it can't be perpendicular is, suppose that, that's a really good question. Thanks for bringing it up. Suppose that I assume that the electric field here was not perpendicular, and I say that it has some component that points parallel to the surface, like this. We can call it E parallel. And it has some component that points perpendicular to the surface right here that we can call E perpendicular. And we think about what effect that would have. If there was a parallel component to the electric field right here, then any charge that's located in here, like let's say we look at this charge right here, it would feel a force in that same direction. That force would be equal to Q multiplied by E parallel, right? That's the force that you'd get acting on this charge. And then as a result of that, this positive charge would be compelled to move to the right. And assumingly, if you had such a component like that for all the charges, they would feel a force that would kind of project them around in a circle. And you get a situation where you have the charges kind of circulating around the outside. And then it would no longer be a static situation. Does that make sense? And so maybe you could argue, okay, well, maybe some places the electric field has a component that points to the right, and some places it has a component that points to the left, and then still you're going to get some net field at some point that's going to cause these charges to move. And if they're moving, then they're not in equilibrium. So the only way to not have them move is to have the component of the field point this way. The other reason, and I guess I was skipping that, so I'm really glad you mentioned that, because that's part of this I'm supposed to prove. But the other portion of that I was leaving out is I was just thinking about this problem. We already know that as long as you get close enough to any surface, it looks like an infinite sheet, right? No matter what the surface is, no matter how curved it is, you get close to that surface right here, and it's going to look flat, right? Just like the surface of the Earth. You get close enough to the surface of the Earth, and it looks flat. So if you zoom in far enough, there's going to be a way you can see it so that it looks like an infinite sheet, so it starts to look like exactly like what we did in this problem, basically. That's kind of what I was thinking. But it is important to consider that it's not possible to have this component right here. You have to only have the perpendicular component. Okay? Okay. Do you guys have any other questions? You ready to take a break? That is kind of the end of the chapter on Gauss's law. We're going to move into talking about electric potential and voltage for the rest of the class. I'll wait for you guys to ask questions before we stop. you guys don't have questions, that's fine, I guess. Alright. So let's take a break until like 7:10, I guess.